So if you look at clouds and ask what runs well in them, here is a relatively simple analysis which will be expanded in these various talks we're having. What I call pleasingly parallel applications, which are these loosely coupled problems illustrated by the Large Hadron Collider, which is independent events, or illustrated by smartphones with their independent accessing of the clouds to do searching or back up their data and things like that. Those are pleasingly parallel problems. There are huge numbers associated with them because there are a huge number of events on the Large Hadron Collider and a huge number of users of smartphones. An important area which we'll have a lot of discussion of tomorrow and implicitly throughout the conference is data analytics, because it will turn out that, as in fact is illustrated by information retrieval, which is one of the world's largest data analysis problems, data analysis has got a different communication pattern to simulations, and that communication pattern is quite suitable for clouds. It tends to have large messages, and these synchronization overheads are not so important. So you can ask who's using science applications are using clouds, and I'm pleased to tell you not very many at the moment, which means that all you here have got a huge opportunity to lead the use of clouds in science, and you're bound to succeed, as I said. The clouds are 100 times the leading supercomputer in that power. And we will see tonight. We will see throughout this summer school many applications. We have 3 Pacific talks on life sciences this afternoon, and each of the sessions will have particular applications described. In particular, this afternoon we'll hear about bioinformatics, high energy physics, nuclear physics, astronomy, and ocean sciences from the Nimbus team in Chicago. One example I have here is from Europe, which has at least got probably the largest single project, the so-called Venus C project. They're using the Microsoft commercial cloud, and they've got 27 separate applications running on clouds. And these are sometimes called the long tail of science. So when you plot usage, if you look at the usage of computing or the size of problems being solved in science, there are a few projects which have huge use, but there are lots of projects with modest use. And so a good example, again, is the Large Hadron Collider. Each of those experiments has thousands of scientists attached to it, and they are huge efforts, each requiring an enormous amount of computing, hundreds of thousands of servers. However, there's many areas of science, which are illustrated actually on this slide, where you get say individual biologists or individual environmental scientists analyzing that data and doing it roughly independently, and maybe comparing with other people's data stored in data repositories. So that's very natural for cloud, because those individual scientists are loosely coupled and not the tightly coupled people who are trying to solve a single problem. And those loosely coupled usages are natural for clouds. So clouds are well suited to what this so-called long tail. So that's basically said here, that the simplest use of clouds is what either has parallelism over users, those are all the different smartphones, or parallelism over usages, which is actually illustrated with a Large Hadron Collider, where an individual experiment submits millions of jobs, each job of which analyzes some of the events in that experiment. So to the cloud, they look much the same. The cloud doesn't really care whether the million jobs it gets are from a million different users or one user submitting a million jobs. I've already referenced smartphones, and this is more generally called the Internet of Things. So the claim is, from the same reliable, if you go to the web and you can think carefully, you can get reliable information. So it looked to me plausible that there will be 24 billion devices on the internet by 2020. So that's the Internet of Things. So each of those things has an IP address, and it's either a gaming device or a sensor or what have you. And so this is a very important, interesting use of this. And each of those things is naturally supported by clouds, because every one of those 24 billion devices will get its intelligence from the cloud. It itself will have the minimum, will have very modest, may have a single ARM chip or something like that, or even an FPGA or something, some very small computing capability, just to do enough computing, and more importantly, to access the world's data to see where their information fits in context. All those 24 billion devices will go to clouds, which will supply them that information. So that's what I sometimes call sensors as a service. And I will skip over these slides so we get the, don't take too long. So here's an important example of this. Google has a very big effort on cloud-based robotics. This is from I recommend the talks of a fellow called Kufner, who's at Google and CMU, and he has several excellent talks on cloud-based robotics. And here the idea is the same. Robots can have modest intelligence built in, and if those robots want to respond in a millisecond, they better make that decision on the robot. But if they're willing to wait 500 milliseconds, they can go off to a cloud, get 100 times the computing, a trillion times the data, and make that decision. So cloud-based robotics is a very important area, likely to be a dominant trend in this area of robotics. And I'm trying to persuade local people here at IU to get interested in this.